Hello, students. This is Chapter 10, Chapter 3, Solving Quadratic Equations. If you hear any kind of crazy noises in the background, that is because I'm recording this outside. That's the only option I have available to me right now, so enjoy the background noise. We are going to start off on your classwork side. And make this little video here. Come on now. There we go. On your classwork side, now normally we skip over the skills check section, but considering the situation we're in, it's not a bad idea that you go ahead and give the shot. I will go over these there as well. All right, not now. So go ahead on your classwork side, copy those down, show any necessary and the solutions there. So vocabulary that is going to either introduce or clarify during this section: quadratic equation, standard form of a quadratic equation, roots of the equation, and the function. Activity. So I don't expect you to do the activity, but I'm going to use the activity for this. We are very comfortable with y-intercepts in both linear and quadratic functions. Linear functions, especially when they are written in y equals mx. Usually one of the first points that you graph is the y-intercept because it is just sitting there for you, staring in the face. Get the pointer. There we go. So it's just staring at you, -3. You graph that bad boy, use your slope, you got your line, you're good to go. Quadratic equation, similar situation. We see this value here. We know if x is 0, that's going to be our y-intercept. We graph it. Now, just using a slope to find the next point is not quite so easy. The symmetry from there. But as far as y-intercepts go, we're pretty good. What we're going to focus on instead is this intercept in this form of a linear equation. It's not very obvious what that is or how to get it, other than you just go, all right, I'm just going to substitute a 0 for y, which is going to get to in a second. Which is what you do in the standard equation. But in the standard form of the equation, substituting 0 for y, we almost always end up only one step, if not 0 steps away from getting x isolated all by itself, and the x-intercept. In this form, it's a bit different. So here, there's not an obvious way. Once we substitute 0 in for y, there's not an obvious way to find out what our x-intercepts are. So for this section of our work, we're going to look at very specific quadratic equations so that they want you to think about y for the whole section, not just now, for this whole section. You're going to notice a pattern that all quadratic equations that work with have a value of 0, which means there's no term. There's a reason behind that. And what we're instead going to do primarily is look at the graph. And we're going to say, okay, here are the x-intercepts, and we're going to make sure that those x-intercepts really do represent when y equals 0 by substituting them back into the equation. So I'm not going to bore you with this. Well, that's not a great way to phrase it. I'm not going to spend a lot of time going over this. This basically shows how you substitute 0 for y and verify that your x-intercept, or solve for your x-intercept in the case of the linear equation, does actually produce a y value of 0. All right. Part 4 gives you a different equation, a different function, excuse me, to graph and find the intercepts and then test the intercepts. If we were in class, we might do this activity right now. Just and you tested your x-intercepts, that would make this function equals 0 right here for y. All right. So what is the difference between a quadratic equation and a quadratic equation? Is when we take the quadratic function and we substitute in 0 for y. This is this is the very specific equation that we are going to use to find the x-intercepts, which are also known as the roots of the function. If you think of roots where a plant touches the ground and then, beneath that is where the roots start. That's kind of a similar thing here. Our roots are where we go from above the x-axis to below the x-axis, all right? So we're looking for roots when we're using the quadratic equation, because with the quadratic equation, 0 is substituted in for y in the function, or we're looking for the function of x when x is 0, all right? No, I said that wrong. Oh, when the function of x is 0. So we're looking for the x values when the function of x is 0. So that's if we saw an f of x instead of a y. All right, so hopefully that wasn't too confusing. The quadratic equation is when we have our quadratic function equaling 0. Quadratic function is when we still have y, or f of x, function of x, there, and that represents the entire function. All right, not just when y equals 0. Okay, let's go on to the quick checks. Here is an explicit definition of the roots of the equation, or the zeros of the function. And here again is the definition of a quadratic equation, and of course the standard form of the quadratic equation, ax squared plus bx plus c. And you will again notice that in this section, b is going to be 0. We are not going to worry about that middle term. Very specific reason. Again, I want you to think about why. Example 1, solving by graphing. So now you are expected to graph the function, and in that function, find where the curve crosses the x-axis, identify those as your roots, substitute them back into the equation to test and see if those are truly the zeros of the function. All right. You're going to run into 3 scenarios. 1, there are either 2 roots, 2 zeros. There is 1 0 when the curve comes in and just clips that x-axis, and your vertex is on the x-axis. You're only going to have 1 solution to the equation. Or if your vertex is above the x-axis and your function is positive, which means the curve is pointing up, then you are going to have no solution at all. And I want you to think about what the equations might look like for these different possible scenarios, not just these specific equations, but what kind of features might they have in general that would help you predict whether you are going to have one root, 1 solution, solutions, or 2 solutions. Okay, so quick check is going to ask that you go ahead and graph these 3 functions and determine whether or not there is a solution, 2 solutions, or no solution. Now we're not going to graph. Now we're actually going to solve quadratic equation. So something here, go ahead and read this reminder to yourself. When you're finding the square root, typically your is to give the positive value of the square root of a number. In this case, the square root of 36, you might just simply say 6. Well, square root of 36 is also negative 6. And it's important to identify that negative value, because that is going to be where a curve hits the x-axis on the other side of symmetry. Again, we're working with functions. The 0, there where the axis is our axis of symmetry. Every single time. Okay, so the equation you can only graph. You guys know how to add to both sides. I'm going to go ahead and divide by 2. We end up with this perfect square here, 49. Take the square root of that in order to find x, and we see that our solutions are positive and negative 7. If you were to graph this, the function would cross the x-axis at both negative 7 and positive 7. So Here, a quick check. We are to ask you for these three problems. I will let you know that one of them is going to put you in a spot where you have to find the square root of the negative number. I need you to figure out what that means in our one of three scenarios. One solution, two solutions, or no solution. Muy bien. Last question. Here, we have to apply our understanding of quadratic functions and equations in a real-world scenario. Now, here's nothing about the math. The only thing that you have to worry about is in a real world, solutions are reasonable. All right, we'll get to that here in a second. So we're talking about a circular duck pond. If it's a pond, that means it's three-dimensional. Circular describes the shape of the surface, so therefore we are most likely working with a cylinder. Go ahead down the givens. We're given a volume. Don't forget your units. We are also given a height or depth of our cylinder of 4 feet, and we are asked to find the radius. So the radius is our unknown. They're giving us the equation to use, which happens to be the volume equation for a cylinder, and definition of our variables. Awesome. They write out the equation, substitute into parentheses, divide both sides by pi and 4. Go ahead and take the square root of this guy, throw it into a calculator, round to the nearest tenths place, and we find that the pond will have a radius of 39.9, not positive or negative 39.9, because in a real world situation, we're concerned, the word, the negative value of the radius. Not taking negative measurements here, folks. So it's a positive radius of nearly 40 feet. That's a big pond. Okay, so in your problem, you are not going to be trying to find the radius of a pond. Instead, it's going to be a circular fountain. Right? It's basically the same problem. They're going to give you the depth, 3 feet. They're going to give you the volume, 1,800 feet cubed, and they're going to ask you to find the radius. Okay, same scenario. Go ahead and ignore that negative value. It is unimportant in a real-world situation. So, three different sections here, folks. Again, specifically when b equals 0, you'll notice that pattern again. Graph from just the equation, and then applying what we know a real problem. With these questions at the in your book, if you have your text, they are on page 567. Text. This slideshow is in classroom. It's a long one, but it takes a while to get done, folks, especially when we're talking about oh, what connecting to I'm outside and I just watched my neighbors do a gender reveal, apparently having a baby girl. Fun fact. So back to the work. Problems 1 through 21. 1 through 9. Now, pro tip. When you're looking at the graph, I need you to don't put them into a calculator to see what they look like before you graph them. Don't just look for features and mental calculations to predict, right? You know where these y-intercepts are. You know where the y-intercepts are. I want to predict what that graph is going to look like. And set up your graph. You do not have a lot of empty space, a lot of irrelevant space in your work just in that quadrant. Okay, so for example, number 1, you know that's -9, so you don't need to show a positive y-axis that goes up to 25. It's unnecessary. In fact, you don't even really need to show much beyond y value. Your text is going to be a 9. It's going to go up from there, and you're specifically looking for where that graph crosses the x-axis. So no need to graph the upper hemisphere, you know what I mean, of your quadrant. Moving. Okay. Here, example 2, please show your steps. Example 3, make sure that you know that those are 3 real-world examples. Therefore, only that are relevant to that real-world situation. All right, so this is the instruction video. You will have a video of me doing all the quick checks, and then a third video of me doing all of the homework. That is going to be your assignment for, I believe, maybe the next 3 or 4 days. All right, anyway, hopefully you're doing well, and we'll be in touch soon.